We can present the molecular geometry and the way the atoms are connected in space using various models. One model is the valence shell electron pair repulsion model, the VS-EPR. The valence electrons carry negative charges. When valence electrons of different atoms form bonds, they repel each other. By knowing the number of valence electrons and the lone pairs, we can predict the angle between the bonds and the molecular geometry of the compound. Let's use the VS-EPR model, the valence shell electron pair repulsion model, to predict the shape of methane molecule. Methane has one carbon atom that has 4 valence electrons bonded to another 4 hydrogen atoms. If you looked at the electron density around the carbon atom, there are 4 equal densities of electrons surrounding the carbon atom, the 4 bonding pairs. For electrons to stay farthest away from each other, the 4 bonds form 109.5 angle between each. The 4 HCH bonds around the carbon atom form a tetrahedral 3-dimensional structure with perfect equal angles of 109.5 each. Notice the tetrahedral shape has a total angles of 438, which is larger than the complete angle 360. You have to remember this is a 3-dimensional structure, which means it is in different planes. So we are not confined by 360 complete angles. Now let's look at the water molecule. Water has 3 atoms, 2 hydrogens singly bonded to a central oxygen atom that bears 2 lone pairs of electrons. Water molecule forms a tetrahedral shape as well, but you can see that the angles differ from methane due to the different degrees of repulsion between electrons. The 2 lone pairs, non-bonding pairs, exhibit the maximum repulsion with the largest bond angle, larger than 109.5, leaving the 2 bonding pairs with an angle smaller than the 109.5. Actually, it is about 104.5. The angle between each lone pair and bonding pair is intermediate, with intermediate repulsion. If you look at the electron density shape on the right, you will find that electron density is concentrated on the oxygen lone pairs. Here is the ball and stick model, shows that the angles around the oxygen are not equivalent. Let's try to predict the shape of ammonia molecule. It has 3 hydrogen atoms bonded to nitrogen atom that carries 1 lone pair. The distortion due to the repulsion between the lone pair and the bonding electrons is maximum, leaving the angle between the 3 bonding pairs smaller than 109.5. Notice the bond angle HNH is equal to 107.3, which is larger than the bond angle HOH of water. The reason is that the repulsion between the 2 lone pairs of water is largest, which squeezes the HOH angle, making it smaller. Let's look at this table together. You can predict the geometry of molecules and the distribution of electron densities by knowing the number of bonding pairs. If the molecule contains 2 bonds, this means the angle is equal to 180 and the shape of the molecule is linear. For example, in carbon dioxide molecule, the COC angle is linear. If the molecule has 3 bonds, the formed shape is triagonal planar with 120 angle. For example, the boron trichloride molecule has a triagonal planar shape. 4 bonding pairs form a tetrahedral with bond angle equal to 109.5. For example, like we saw before, the methane molecule. 5 bonds form triagonal bipyramid. Notice the angle of the atoms on the same plane is equal to 120, and the angle of the atoms out of the plane is equal to 90. There is no much repulsion because they are on different planes. Moving to the octahedral geometry, that occurs due to the presence of 6 bonds forming 90 degrees angles. Also, here you have 2 atoms out of plane and 4 on the same plane.